You just said
biomolecule.
you are not audible clearly. Can you repeat? Firaz.
Yes,
So any topic that you are having problem,
biomolecules like
okay, you want to go for all the chapter because you told me that you have already covered that. That's why I didn't use that chapter. So you want to cover that chapter, right?
no need in depth, just like the important points.
Okay, wait a minute. Biomolecules.
I think like we have to learn that each.
Just wait for a few minutes. I'm gonna cover this. Okay. Let me share one more, another screen, and it will be covered soon. And it is in MEH, I think. Here it is. Okay. And let me know when you are able to see this thing.
Yeah.
Okay. So you can see what is biomolecules. In this biomolecules, first of all, we have three topics to cover. One is your carbohydrates, then comes your uh, protein, and then amino acid. Three topics are there in biomolecules. So first of all, we are going to deal with this carbohydrates. What is this carbohydrate? So initially, the old definition for carbohydrate is the compounds of carbon having hydrate, or we can say hydrate of carbons are called carbohydrates, and they gave a general formula like this is the general formula CxH2O whole Y. Like if you want to write the formula of this C6H12O6, which is basically glucose or fructose formula. So you can see I can write this C6 and H2O whole thrice. Can I write this? Wait a minute. 6 whole 6. So it is just in the form of this, yes or no? You can see the x is 6 and the y is 6. It may or may not be equal to the equal to each other, x or y, depending upon the formula. Is that clear? So at that time, the definition was whoever satisfy this formula will be carbohydrate. But uh, uh, after some time, you will have basically they found that there are some compounds which are satisfying this formula but are not carbohydrates, like this C2H4O2, which is an acetic acid, which is CH3COOH, acetic acid, not a carbohydrate, but it does satisfying this formula. So there will be limitation of this formula, and there are carbohydrates which does not satisfy the this formula, but that is carbohydrates, so it failed. Are you getting my point? Like Ramnoj is having this formula which will not satisfy CxH2O whole Y, but it's a carbohydrate. Are you getting my point?
Yes, sir.
Okay. So, are you able to understand it? Because it's already written. If you have
Yeah.
any problem, then I can write it, but it will take our time. No. Okay. So there is another form definition for this carbohydrate, which is any carbohydrates or any compound which contains aldehyde or ketonic group, either aldehyde group or ketone group with hydroxy group. That means basically any compound which contains aldehyde with hydroxy, that is your carbohydrate. And we can define it like uh, the condition is basically the it can be defined as it should be optically active. As optically active polyhydroxy aldehyde or ketones, or we can say the compounds which produce such units on hydrolysis. It's very simple. If you have a compound having aldehyde and polyhydroxy, that means more than one OH group attached in that compound, and if it is optically active, then it is carbohydrate. Or if you have a compound and if you are going to hydrolyze it, you are going to react it with water, and if you are getting such product, then that compounds are known as carbohydrates. Is that clear? Okay. So are you writing it or you have already the notes? Firaz?
Answer.
Okay. Now see, basically some of the carbohydrates which are sweet in taste, that are called sugars. And you can see the most common sugar used in our home is named as sucrose. And whereas the sugar present in milk is known as lactose. So this can be directly asked in MCQs. What is the name of sugar that is used in our home? That is sucrose. And the sugar that is present in milk, that is lactose. And what is su- sugar? So the carbohydrates which are sweet in taste are known as sugars. Okay. Now I start classification, which is very easy. So it is based upon hydrolysis. If you are going to hydrolyze a carbohydrate, and if you are having after hydrolysis, you are not getting anything, then it is monosaccharides. Monosaccharides, the carbohydrates which does not hydrolyze further. It is already in its simplest form, like glucose, fructose, galactose, etc. are monosaccharide. Its name is very important. This can be directly asked, which one of the following is monosaccharide? Glucose, fructose, galactose, and all of this. So all of this. Oligosaccharide, if you are having a carbohydrate and if you are going to hydrolyze it, and you are getting 2 to 10 units of monosaccharides, then it will be oligosaccharides. If you are going to hydrolyze a carbohydrate and if it gives you 2 monosaccharide, it is known as disaccharide. If it gives you 3 units, then it is known as trisaccharide, and so on. Then 10 units, then known as decasaccharides. So I just wrote here disaccharide 2 units, trisaccharide 3 units, and its name is basically raffinose. So sucrose, maltose, and lactose are the example of this oligosaccharide. Polysaccharide, which gives several units of monosaccharide. Polysaccharide are which gives several units of monosaccharide. Like example, you can see carbohydrates which produce a large number of monosaccharide on hydrolysis. As for example, this starch. As for example, cellulose, glycogen, gums, etc. These are polysaccharides. And basically, these polysaccharides are not sweet. Basically, these are not sweet in taste. That's why they are known as non-sugar. The carbohydrates which are sweet in taste are known as sugar, and the carbohydrates which are not sweet in taste are known as non-sugar. It's very simple, right?
Yeah.
Okay. Now the next is it is based upon reducing and non-reducing sugar. Basically, reducing and non-reducing sugar. There is some reagent like Tollens reagent, Phalanx reagent, and Benedict reagents, it will reduce itself and oxidize the carbohydrates. This is based upon, and the one which is oxidized is known as reducing sugar, and the one which is not, that is known as non-reducing sugar. So the carbohydrate which reduces TR, Tollens reagent, Phalanx, or Benedict, that is known as reducing sugar, and that does which does not reduce these reagents are known as non-reducing. For example, this is sucrose, and here you can see the example of monosaccharide like glucose, fructose, galactose. These are all reducing sugar, and disaccharide like uh, maltose and lactose. These are also reducing sugar. That means it will reduce following reagents. So first of all, we are going to take this tolerance reagent. So what is this tolerance reagent? Basically, it is ammonical silver nitrate. It is ammonical silver nitrate. So either you can see, either you can take this, or see, if you are going to add this, you will be getting this compound, which is complex compound or Ag plus. Basically here in ammonical silver nitrate or tolerance reagent, the oxidation state of Ag will be +1. And if you are going to add this compound, or the compound which is having Ag oxidation state of Ag as +1, so what will happen, you can see, if you are going to, carbohydrates will oxidize and Ag plus will reduce itself, and this, since this will reduce itself, that's why it is known as reducing sugar. Are you getting my point? What you need to do, you just need to take a carbohydrate and mix this with fresh ammonical silver nitrate. If this silver nitrate or silver will, you'll see silver will be reduced, then it is reducing sugar. The carbohydrates that you have used is reducing sugar. In the same way, you have Phalanx reagent, and Phalanx reagent is also going to do the same, only the reagent will change. In this, we have two container of the, we have two container for Phalanx reagent, and this is known as Phalanx A and Phalanx B. In Phalanx A, you will use this aqueous CuSO4. You will use aqueous CuSO4, and basically when it will be present in water, it will be in the form of CuSO4.5H2O, which is known as blue vitriol. Are you trying to say anything, Firaz? Because you are muting and unmuting yourself. Okay, just let me know whenever you need another explanation. Okay. Okay, thank you. So in Phalang A, we have this, and in Phalang 2, we have Russell salts, which is basically sodium potassium tartrate. So what you need to do, just mix this in equal amount, and then a carbohydrate. If this will be reduced, so you can see Cu is in +2, this will be reduced to Cu, then this is known as reducing sugar, the carbohydrates that you have used. In the same way, you have Benedict's reagent, same as Phalanx reagent. Here you took mixture of aqueous CuSO4, and here you took sodium citrate. Mix this in equal amount, and then carbohydrates. So what will happen here? You are going to reduce itself. If the carbohydrate reduces it, generally then it is reducing sugar. If it is not, then it is non-reducing sugar. I already gave you the example of reducing and non-reducing sugar, which is very important. Now come to this point, classification based on carbon atoms. So if aldehyde group is there and having 3 carbon and it is a carbohydrate, then it is known as aldotriose. And if at the place of aldehyde, if you have ketone, then it is known as ketotriose. So for 4 carbon, first aldo, for if Aldehyde is present, we use aldo. Ketone is present, we use keto. So aldotetrose, tetro, that represents 4 carbon, ketotros, aldopentose, ketopentose, aldohexose, ketohexose, and this aldohexose is your, you can say, glucose. This is the most famous, and it can be fructose. Is that clear? The formula of glucose and fructose are same. Only the difference is that in glucose we have aldehyde group, and in fructose we have ketonic group. Now, how we are going to prepare this methods of preparation of glucose. So the first method is from sucrose. So if you're going to hydrolyze sucrose, you will be getting glucose and fructose. Since on hydrolysis of sucrose, you are getting 2 units of other monosaccharide. That's why it is disaccharide. It is also very important to note that if you're going to check optical property, optical activity of this sucrose, you will see it is dextrorotatory, which means positive. And on hydrolysis, you have seen the glucose is also dextrorotatory, which means clockwise and positive, and it has a value 52. And fructose has a negative, which is levorotatory, which has a value minus 92. So if you are going to add this, the net rotation will be in negative because the value of negative is greater, and you can see the net rotation on the left hand side is positive, net rotation on the left hand side is negative. That's why this reaction is also known as inversion of cane sugar. This reaction is also known as inversion of cane sugar. And the enzyme that we use, or we say this is your invertase. This is your invertase. Is that clear? This point is very important. Why it
Yeah.
is known as inversion of cane sugar? Because the net rotation on the product side will be in negative. Very
Yeah.
good. Now from starch is a polycarbohydrate or polysaccharide, you can say. So you just need to do the hydrolysis. You will get n molecules or n moles of aldehyde, aldehydes, glucose. Properties of glucose: glucose is dextrose, that means uh, dextrorotatory, clockwise, positive sign D. And it's also very important to note that this is the Fischer projection of glucose. So this is how we write glucose, and this is your Fischer projection, which is very, very important. I would like to ask you a question. Can you count the number of chiral carbon here? How many chiral carbon does this have? Do you know what is chiral?
4.
4. So what is the condition for chirality?
Should be optically active.
Only this condition?
The
How do
mirror
you know?
image has to be symmetric.
Okay, tell me something that you can do theoretically. Optically active or not active, that you can also do by checking the POS and TOS, right?
Yeah.
There should be something that mm, this see the best part or the easiest part is just check the carbon is sp3 or not. If the carbon is sp3, that is well and good. This is the first condition. And the second condition is all 4 group is different, should be different, must be different. Are you getting my point? So if all the groups are will be different, the mirror image will not be possible. Are you getting my point?
Yeah.
Very good. Now see. So this is this carbon chiral? Yes or no? If it is not, why it is so? Can you tell me?
3.
No, three. What you just said. Three. Why? I'm asking you. Is this carbon chiral? Yes or no? You gave
Yeah.
me the answer. That is right. Is it? Is this chiral?
Yeah.
Okay. This is not chiral. This is CHO. That means C double bond O H, and it is connected with the this. Yes or no? So if you are going to
Yeah.
if you are going to do the hybridization of this carbon and it's making a double bond, that means it is sp2. So it just violated the rule to be a chirality.
The one after CHO, that'll be HP.
Yeah, this will be because you can see this group is different, this group is different, this group is different, and the downward is it's entirely different. So it is chiral. This is also chiral because this is different, and above this carbon is also different, and below this is also different. So these are all chiral. So that's why I wrote here total number of chiral carbon is 4. And this is the prime condition. So please keep it in mind because it's very important for other chapters too. In the first chapter, that is more important. Okay.
Yeah.
Now see, chemical reaction, it's very easy if you have studied all the reaction from aldehyde. So we are going to see the chemical reaction with HCN, and in this chapter we are only dealing with glucose. So you know that in glucose you have polyhydroxy, and the main functional group will be basically CHO, which is aldehyde. So basically aldehyde will be reacting with this HCN, and we have done this reaction cyanohydrin. Do you remember when we did chemical reaction of aldehyde and ketones? Are you getting my point? Yes or no?
Yes.
If you don't get it, just let me know. So how I just gave you the overview of this reaction, how the reaction takes place in with cyanohydrin. So this is aldehyde or ketone you can take as, and if it is going to react, CN will have negative, this will have positive, so it will be like this. And in the same way, this is the basically mechanism. So how it is going to react it with glucose? So you can see here it is. So it will react with this. And now after reaction, there will be 5 chiral carbon in this. So the reaction here is very easy and important. If you still have any doubt, please ask. Can I change the slide?
Yeah.
Now, reaction with HI or red phosphorus. This chapter is also important because of its this reagent, which is already I have written here. What is the function of this? HI red phosphorus is basically very strong reducing agent. So you have to keep it in mind the property of this reagent. So what it will do, basically, it will reduce all this. So you know this is your aldehyde. So it will be reduces, and how it is gonna reduce? So it's very easy. I'm gonna show you. So you have seen this all the bond reduced. That means addition of hydrogen, removal of oxygen. So you can see H2O will be removed. Here it becomes CH and H is there, and this H will combine to form CH3. So basically, when you are going to use this, the glucose will be converted into normal hexane or N hexane. Is that clear? Even this LiLH4 does not have tendency to reduce alcohols, but this is so strong of reducing agent that it can reduce these alcohols too. So I think you have got it. If you are having any issue in this, please do let me know. Can I change this slide?
Yes.
Are you done with this?
Yeah.
Okay. Now see if you are going to react this with hydroxylamine. So see, hydroxylamine NH2S, this reaction you have already studied it in the aldehyde and ketones. So how the reaction will take place? You just need to remove the water part and connect this carbon to this nitrogen. So in the same way we just did it, and this is known as glucose oxime. It doesn't react with alcohol, so you just need to do this and you will get glucose oxime. Are you getting my point? If you have ketone, you just need to do the same. Just was see the reaction. If you have any doubt, just ask me, or if you don't, let me know so that we can move to the next. Mm. And let me know when to change this, right? You have notes of this, right?
Yeah.
Okay, can I change the slide?
Yes.
Okay. If you don't get it, just let me know. I will write it. Reaction with this bromine water. And I have written here its function. That is basically mild oxidizing agent. It is mild oxidizing agent. So what does this mean? Means mild oxidizing agent. It will oxidize aldehyde to ketone and the rest part, I'm sorry, aldehyde to carboxylic acid. It cannot oxidize alcohol because it is mild oxidizing agent. So the aldehyde part will be directly converted into carboxylic acid, which has a name which is quite famous, and that is your glucaric acid, or we also say aldonic acid. So in this reaction, total 8 reaction, we just you just need to deal with the reagent. You just have to remember what this reagent do, what its actual function, and by doing this, you will cover also the aldehyde and ketones group. Are you getting my point? I also have written here a very important point. Only oxidize, only oxidize this aldehyde, but not alcohol. Just let me know. Let me know when you are done with this. Can I change the slide?
Yes.
Now see next reaction with this concentrated HNO3. What's its function? So it will convert aldehyde. It is a oxidizing agent into carboxylic acid, and it also oxidize alcohol, primary alcohol to carboxylic acid. So if you have secondary, it cannot oxidize secondary alcohol. It will only oxidize this part, this part. So you can see it is mild oxidizing agent. You can see aldehyde can be converted into carboxylic acid and also 1 degree alcohol. So this is your 1 degree, and all the alcohols or hydroxy group are basically your secondary alcohol. So this will be converted into carboxylic acid, and this 1 degree alcohol will be converted into carboxylic acid, which has a name which is known as glucaric acid or saccharic acid. Is that clear? So it's very important the reagents you are going to deal with. Please do this reaction. It will also strengthen your aldehyde chapter. Okay. Now, when you are going to do reaction of this aldehyde with acid anhydride, basically not a aldehyde. Basically, if you are going to react this glucose, which has polyhydroxy group, with acid anhydride. So you have seen when you are going to react alcohol with acid anhydride, there will be formation of what we say, there will be formation of ester. That's why it is known as that's why it is known as esterification. The reaction is known as esterification. So you know this is alcohol, so it will have positive charge, and this will have negative, this will have positive. So you just need to change it. So this alcohol hydrogen, the alcohol's hydrogen will be replaced by AC group. AC is your acetate, this group. AC is your this group, acetate group, this group. What I was telling, this group. So every alcohols or polyhydroxys hydrogen will be replaced by acid, and this is known as your what we say, glucose pentaacetate. This is known as glucose pentaacetate. So it's also very easy and very important. Is that clear?
Yes.
Okay. Now the next reaction is basically the same reaction. If you are going to react this with concentrated HNO3 glucose, you will get glucaric acid. And if you are going to use this gluconic acid and a concentrated HNO3, so what does it do? It convert primary alcohol into carboxylic acid, or it also convert primary or aldehyde into carboxylic acid. So the both reaction will lead you to the glucaric acid. Both reaction will lead you to the glucaric acid. So it's very, very easy. Now, the next reaction, which is very important, and this is your osazone formation. And for osazone formation, we use 3 moles of phenyl hydrazine. What is phenyl hydrazine? So this is your phenyl hydrazine. Hydrazine is your NH2NH2, and if you are going to remove one of the hydrogen and connect to pH, that is known as phenyl hydrazine. So we are going to use the first mole of phenyl hydrazine, and in the first mole of phenyl hydrazine, you are going to remove water. So this is formed. After formation of this compound, you can see hydrazine, phenyl hydrazine, you just remove water and you got a this product. So for the osazone formation, we need to use 3 moles of phenyl hydrazine. So we use the first mole of phenyl hydrazine. Now the second mole of phenyl hydrazine will be used in this, and this is also an oxidizing agent. So what will happen? It will attack on this part, and this basically secondary alcohol will be converted into ketone. The secondary alcohol will be converted into ketone in this way. So you can see the product is here, which is oxidized to ketone. In the second step, you have seen that a redox reaction took place. Why redox reaction? Because it oxidizes, so something will be reduced. So this is the second step. In the third step or third mole of phenyl hydrazine, which we are going to use in this. So you can see in this, again, there will be removal of water from this ketone, and this is your known as osazone. So always remember, for osazone formation, you need to use 3 moles of phenyl hydrazine. Is that clear? It's very, very important. Can I change the slide? Let me know.
Done.
Very good. Okay. The next reaction is basically periodic acid, or you can say it is periodic acid, which is oxidizing agent. So see how the oxidation will take place. You just need to break the bond and add water. If one carbon will having two hydroxyl group, which is unstable. So there will be removal of H2O and it forms carbonyl compound. So you can see alpha diketone or alpha carbonyl diketone, that means two ketonic group. So in this way, it will be converted into carboxylic acid. If you have alpha hydroxycarbonyl in this way, so there will be formation of this, and one of the carbon you can see two H group, so there will be removal of H2 and it also forms carbonyl compound. So always remember, it is unstable to having two OH group on the same carbon, so you just need to remove water. So we are going to do this for iodic acid. So you are going to break every bond between carbon carbon. So you removed here and here you will get C double bond O and here H, and you can see OH is there also. So there will be formation of carboxylic acid. So from this carbon to this carbon, you will be getting HC double OH, which is carboxylic acid. HC double OH, which is carboxylic acid. And at the last part, you will be getting HCHO, which is methanol. How you got this? So you can see at this carbon, you are having two hydrogen and one OH, and there will be formation of one more OH. So you are going to remove this H2O. You are going to remove this H2O. So it will become, there will be double bond between carbon and hydrogen, and it in this way it forms methanol or formaldehyde. Let me know when you are done with this.
Yes.
Very good. Reduction of glucose. That means you are going to use this. You are going to reduce this, and whether we will use LH, which is lithium aluminum hydride, and SPH, which is sodium boron hydride, which is a reducing agent. So basically, it will reduce aldehyde into alcohol, and this compound is known as s orbital, or you can call it s orbital or sorbital. So this is how reduction will take place here. Are you done with this, Firas?
Yeah.
Okay, so see the next reaction. It is basically the properties, the reaction completed here. So, do you have notes of this chapter or I have to send? Please let me know.
You can send this.
Okay, by tomorrow you will get it. So you can see this glucose and fructose can be distinguished by bromine water, either or this and this three reagents. And this will be reduced by the aldehyde, that means glucose, but cannot be reduced with this. Okay. The next is basically glucose, fructose, and mannose give same OSA zone because in OSA zone formation reaction takes place at first two carbon. So basically the OSA zone formation in glucose that you have seen, that will be same in fructose as well as mannose. Okay. OSA zone is also stable by intramolecular hydrogen bonding. So I hope you know what is intramolecular hydrogen bonding. Do you know that?
Between the molecules of the same.
Same, same molecule. In the same molecule, if there will be hydrogen bonding, that is known as intra.
Yeah.
And if between two molecules, then it is inter. Now, glucose, fructose can be converted to ethyl alcohol if you are going to ferment it in the presence of zymase enzyme. So these are some properties of this. So also it's important glucose does not give this uh, NHSO3 test. Glucose does not give a Skiff's test. Pentacetate does not react with NH2OH that we had found. Now, there are some questions which is also very important. You can read it. Non-reducing sugar. Which of the following compounds is found abundantly in nature? That is cellulose. It present in plant and animals both. Cyclic structure is very important. Do you have any doubt in cyclic structure? Yes or no? Please do let me know.
This is the same one, right?
Same one, that means
We need to learn this Fisher projection.
Fisher projection you need to learn, but the cyclic cyclic structure you can derive like this. You can see this
Yeah.
is your this will be negative, there will be positive, and then there will be positive, there will be negative. This hydrogen will move to this oxygen in this way, and then you are going to count the number of carbon. This will There will be bonding between this carbon positive and this oxygen which has negative. And see how we are going to do. It's very important. Haworth projection we say. So see what I'm going to do. One, two, three, four, five, and the sixth is basically your this oxygen in the ring. Oxygen in the ring. Why it's not working? Wait a minute, please. Okay. So see, I'm going to show you this carbon. Okay. This is the first carbon which is having whatever is on the right hand side of Fisher projection that will be written on the bottom, and whatever is on the left hand side that will be written on top. Are you getting my point?
Yeah.
Now on the second carbon you can see OH is on the right, that means it will be written on the top, bottom, and then left that means top, and right that means bottom. And when you come to the fifth carbon which is having CH2OH, you can see this O is here, so you are not going for this. The another group is at bottom, and the other group is at on the left. So how you are going to do it? You will be going to do it with the molecular weight. Which one will have more molecular weight? This. So it will be on top and the rest will be on the bottom. So this is the structure. This is the cyclic structure of glucose, which has a name alpha. Basically, there is two isomers, alpha and beta, and it depends upon the first carbon. If hydrogen is on the left hand side, it is alpha, and if you are going to change it to the right hand side, it will be beta. So if you are going to change this H to right hand side, the H will be on bottom. Are you getting my point?
Yeah.
So alpha D. D is basically, you can see what is this? What does this D means? D means basically if OH on the right hand side of on the last chiral carbon, this is your carbon. If this is on the right hand side, then it is called D, and if it is on the left hand side, then it is capital L. So alpha D positive because it is dextrorotatory, and glucopyranose because it is similar to pyrene. That's why its name is gluco is for glucose, and pyranose it is similar to pyrene. That's why. So its structure is very important. I would recommend you to write it. Oh, wait a minute. Please do. Are you done with this?
Yes, sir.
Okay, so this is the cyclic structure which is very important. And as I already told you, if you want to draw the structure of beta, you just need to change the position of H. If it is on the left hand side, yeah, it was on the left hand side in alpha, so it will be on the right hand side. So in this way, if it is on the right hand side, it will be at bottom. So this is your beta. And alpha beta are known as anomers, and it is C1 anomers. C1, that means this is the changing place of the bond that is on the left and right. That's why it is known as C1 anomers, switching position. And anomers are diastereomers, no mirror image. Diastereomers, that means no mirror image. All anomers are diastereomer, but all diastereomers are not anomers. This is very important point. Can I change the slide? Can I change the slide?
Yeah.
Okay. Then C for the cyclic structure of fructose. This is the Fischer projection of fructose. Wait a minute, it's not working again. Okay. So you just need to move this and you will get this. And if you are going to count the number of chiral carbon in non-cyclic, you will find that it will be 1 to 3 chiral carbon, but in cyclic, it will be 4 chiral carbon. It will have 4 chiral carbon. In the same way, if you are going to calculate the chiral number of chiral carbon in Fischer projection of glucose, you will get 4. And in cyclic Haworth projection, you will get 5 chiral carbon. So if you are going to draw the structure in the same way, the one which is on the right will be at bottom and and the one which is on the left will be at top. So in this way, you can draw the structure of fructose, cyclic structure of fructose, and it has a name again, alpha D negative because it is levorotatory, and fructofuranose, fructo because it is fructose, and furanose because it is similar to furan. And also, what is this alpha? It if it in on the first position, if you are going to change the position, it becomes in beta, and at the last, it will be on the basis of molecular weight. Is that clear?
Yeah.
So if you just change the position of this, so you can see, uh, wait a minute, you can see OH are now on the top and CH2OH on the bottom. And this is your C2 anomers because the changing position is switching position is 2. That's why it is C2 anomers, and this is your beta. This is also very important. You can see. So alpha and beta forms are called anomers. Anomers are also called diastromers. All diastromers are anomers. That is false, but all anomers are diastromers. And the equilibrium between alpha and beta form is called mutarotation. This is also very important. Just let me know when you are done with this. Done. Are you done with this?
Yeah. Yeah.
Okay. Now, a structure of sucrose. How we draw the structure of sucrose? So basically, when you are going to combine alpha D glucose, when you are going to hydrolyze this sucrose, you will get fructose as well as glucose. So when you are going to combine this uh, alpha D glucose and beta D fructose, okay, and you are going to remove this water, you will be getting the structure of sucrose. So you can see, I just wrote the structure of this alpha D glucose and this is your beta D fructose. So you will be getting this. How you are going to get it? You just need to remove carbon. This is the first carbon, and in this is the second carbon. From here, you are going to remove this H2O, and you will be getting this structure. And this O and this monosaccharide, and this monosaccharide is known as glycosidic linkage. You also need to remember the position C1 and C2. This is known as C1, C2 and glycosidic linkage. It can be directly asked glycosidic linkage. So this is your monosaccharide. This is also your monosaccharide, and O between these two, that is known as glycosidic linkage. Please look at it and let me know. Let me know when you are done. Are you done with this?
Yes.
Okay. So in this way, we have some compounds like a structure of maltose. You just need to remember what is how it forms. So if you are going to combine alpha D glucose and alpha D glucose, that means 2 moles of this. So you can easily draw the structure of alpha D glucose. Yes or no? You can draw it, right?
Yeah.
Okay. And then you are going to remove water from C1 and C4. Then there will be glycosidic linkage present between C1 and C4. So this is the structure, and you can fill the rest of it. Like what is the here? Are you getting my point? HOH, top bottom. Got it? Yes or no?
Yeah.
Okay. So in this way, this is the basically structure of your maltose. I will be sending the notes by tomorrow. Are you done with this?
Yeah.
Okay, see, the next is basically the structure of lactose, and lactose is disaccharide. How we are going to form it? If you are going to next the structure of beta D galactose and beta D glucose. This is the structure of beta D galactose, and this is C1 and this is your C4. C4 from beta D glucose. And if you are going to remove H2O, there will be formation of glycosidic linkage, and then that is known as basically your what we say galact lactose. Please do write it, it's important. Are you done with this?
Yes.
Okay, so you can see this the glycosidic linkage present at C1 and C4. Now the structure of a starch, and starch is basically your polysaccharide, and it has two components, amylose and amylopectin. You need to take care of these two. What is the difference between amylose and amylopectin? Amylose is basically linear polymer of alpha D glucose. That means there will be linearly arranged like this alpha D glucose, and it is polymer, so it will be a lot of several. In this, 15 to 20% starch present. In this amylopectin, 80 to 85% starch present. Whereas in amylopectin, there will be branched polymer of alpha D glucose. That means something is like this, and there will be alpha D glucose in the branch. Here it is water soluble amylose. Here it is water insoluble, which is amylopectin. Glycosidic linkage present here is at C1 and C4, and glycosidic linkage present here is at C1 and C4, and the branch is at C6. Are you getting my point?
Yes.
So you can see this is the differences. Can I change the slide? Can I change the slide?
Yeah.
Okay, okay. So you can see amylose linear polymer. So linearly it will be arranged like this: alpha D glucose, alpha D glucose, alpha D glucose, and then there will be removal of H2 in this way, and there will be formation of glycosidic linkage. And this linkage is known as alpha link because it forms from alpha D glucose. That's why it is known as alpha link. Okay. Also, it's important that this glycosidic linkage is present at C1 and C4. This is the C1 and this is your C1 and C4, C1 and C4. So this is your amylose. Okay.
Yes.
Now, when we move to the amylopectin, there will be branch at C6. So I have written here, this is known as basically glycosidic linkage. Alpha links are present at C1 and C4 in amylose. When we talk about amylopectin, you know that branched polymer of alpha D glucose and glycosidic linkage, which is known as alpha links, are present at C1 and C4 in this and branch at C6. So this is your alpha links, the glucose from alpha links, and the another this is another which is going to have branch. So you can see this is the first carbon, and you can see 1, 2, 3, 4, 5, and this is the sixth carbon. So there will be branch between this. So you are going to remove water from here, and there will be a glycosidic linkage, or you can call it a branch. There will be another glycosidic linkage between C1 and C6, and at C6, as we told you, that it will be a branch. So at C6, there is a branch. So amylose is linear polymer, and amylopectin is there is a branch at C6 in this way. Okay,
Yeah.
so this is it for today. And the next is we can say is this the structure of cellulose, and the structure cellulose is also a polysaccharide, and it is basically linear polymer of beta D glucose, only beta D glucose. So you just need to remove water from C1 and C4, and it is beta D glucose, and you will directly get the structure of this cellulose, and this is known as beta links because it is prepared from beta D glucose, and the linkage glycosidic linkage is between C1 and C4. So this is all about the carbohydrates. In the next class, if you are going to join, then we are going to talk about the what we say uh, proteins and